Okay, so very short lecture today, which is good because at this point in the course, you're probably ready for a short lecture. So today we're going to talk about the failure of brittle materials, and the next three lectures are all talking about failure of materials, but we'll start with brittle materials, and this is really taking the combined loading and stress transformation knowledge that you now have and using those to predict when a material will fail. So brittle materials like concrete, cast iron, chalk, these are materials again that can experience very little deformation before they fail. So let's do the let's look at a piece of chalk, and if you've got a piece of chalk at home, you can try this. Not as easy to come by, maybe unless you've got kids as they used to be. But what you do is you take a piece of chalk and you subject it to a torque couple like this. So if you very carefully make sure that your chalk is only under applied torque, so you're twisting it at either end without pulling on it or bending it, then what you will find as you increase that applied torque, when the chalk breaks, if you look at the fracture surface, you will find that the fracture surface is oriented at 45 degrees to the horizontal, and that will occur every time. That fracture surface will be oriented 45 degrees. So what I want to, this is the fracture in chalk. So what I want to explore here is why does that fracture develop at 45 degrees? So let's assess what the stress looks like at some point along that fracture line. Let's say point A here. Now we'll do a section cut through point A as we normally do, and then figure out what the stresses are on the volumetric element, plot Moore's circle, and then rotate the element to get the orientation of the stresses at a 45 degree inclination. Okay, so taking a section cut through point A as we'd normally do here, get something that looks like this here, where our applied torque is in this direction and our internal torque. So let's get the rest of that cross section. Then we put a set of axes here, one up, one like this, one over like that. And let's make this the X, Y, Z here. So our internal torque is occurring about this y-axis like that. T subscript y is the internal torque. Now, if we draw the volumetric element that's located at point A here, let's do that. Right, so this is the small bit of material that is actually located at point A. And the face of this cube of material that's in the section plane, so the plane that we're cutting through, is the bottom face here. There we go. Now, the torque Ty, internal torque Ty, is going to create a shear stress over this face in the direction of that torque. So we're going to have a shear stress that is like this. So this is tau created by Ty, and we've got an equal and opposite shear stress on the top, and then our complementary shear stress is holding that element in static equilibrium like this. So in terms of our axes, X, Y, and Z. Now, that's the only stress that we have on that element. And it would be the same for any element within the object, with the exception of at the very center of this piece of chalk, which doesn't experience any stress. But for any point around the circumference or moving radially inward, except for the very center, you'd get a volumetric element that looked like this. So if we want to plot Moore's circle, we need to convert this to an in-plane element, which is easy. We can just look at this in the XY plane here. And in that plane, we'd see that this shear stress is upwards, that's down, over, and to the left. And these all have a value of tau ty. Okay, so we can plot Moore's circle now for this element. And if I just do that down here, it doesn't need to be big because it's a small, pretty simple Moore's circle. So plus sigma plus tau there. The center of the circle is always given by the average normal stress. For this in-plane element here, the average normal stress is 1/2 of sigma x plus sigma y, which is 0. So the center of our circle is right at the origin. There we go, C. And then point A, the reference point of the circumference, is given by the stresses that exist on the right-hand side of the element. So we have point A is given by the coordinates sigma comma tau on the element's right-hand side. And these are, let's see, 0, no normal stress, and tau ty here for the shear stress. And it's an upward shear stress on the right-hand side there. So we've got a positive stress tau ty. So let's plot that. So we go down here to, let's say that this is a value of positive tau ty, and put on our reference point, point A. Then the center of the circle connects C to A, and that's a circle of radius r, and draw the remainder of the circle there. Okay. So now let's think about this 45-degree line again. So from where we currently are to rotate the element 45 degrees, let's say that this is a rotation sort of in the direction that the fracture is appearing. So we go from point A, and a 45-degree rotation in the clockwise direction on our actual object. So in other words, we're interested, we started with an element that is normally oriented. Let's say the element, if we put it on our object, is like this. So that's the element that we've analyzed. And instead, what we want to do is we want to look at the stresses on the element when it's being rotated by 45 degrees in the clockwise direction. So a 45-degree rotation on our object, we always double that when we look at the rotation on Moore's circle. So we're talking about a 90-degree rotation, and there we go. So we're rotating all the way here to point A prime. So let's just draw that element and look at the stresses that would be on it here. So, and actually let's just move this over here a little bit. There we go. Then we'll have more room to draw that element. So we've got the element that we've inclined now by 45 degrees. So the right-hand side of the element, right? Our right-hand side was this one. We took this element here and we tipped it up in the clockwise direction 45 degrees. So that is our right-hand side there. The stresses at A prime give us the stresses at A prime, the coordinates of A prime give us the stresses on that right-hand side. So there's a compressive stress acting on that side. So here is sigma, and we'll call that the second compressive stress, or the second principal stress, sigma 2. We know it's a principal stress. Sigma 1 and sigma 2 have the same sign here, so we'll just call the -1 sigma 2. And then on the opposite side of this element, right along that side right there, we get the stress on that side by going from A prime all the way over to this side 180 degrees opposite the circle, and we see that there's a tensile stress there, sigma 1. Okay, so on that 45-degree angle, there was only normal stress existing, and the stress that was separating the material on that fracture line was the tensile normal stress. Okay, so this chalk, when you apply that torque couple, it fails not because of the shear stress that is existing within the chalk, but because of the normal stress, and specifically the tensile normal stress that shear stress creates. Okay, and that's the case for all brittle materials. Brittle materials fail because of normal stress, not shear stress. So let's try that again. Brittle materials fail due to normal stress. And they fail when... So the failure theory for brittle materials is really easy. They'll fail when the ultimate stress divided by the safety factor, if you're using the safety factor, is equal to the first principal stress or the second principal stress. So in other words, if the ultimate compressive strength of the material is exceeded by the largest compressive stress that's in the material, failure will occur. If the ultimate tensile strength is exceeded by the largest tensile stress that exists in the material, it will fail. Okay, so that's our simple failure theory for brittle materials. Okay, so let's do a quick example and show you how this failure theory is applied. Not complicated. Okay, example. So in this example, we are going to have we could do better than that, a concrete column here. Something like this, fixed to a base. So concrete column. And it's, well, let's just show its diameter on the drawing. So let's make it a diameter of 20 centimeters. Okay. And this concrete is going to have the following properties. So it's going to have an ultimate strength in tension of 36 megapascals and an ultimate strength in compression, or an ultimate compressive strength of 6 megapascals. And we are going to say that this column is experiencing a vertical load of 650 kilonewtons and some torque T. And what we want to know is For a safety factor of 1.2, what can the maximum allowable value of that applied torque T be? For SF equals 1.2 max value of T. Okay, so this is a brittle material. It's concrete. It's just got ultimate strengths, no yield. And failure will be dictated by failure of brittle materials, which says that failure will occur when the greatest tensile or compressive normal stresses exceed the strengths, and divided by the safety factor, since we've got a safety factor. So what we need here to start the problem is we need to identify the point in this column that's under greatest stress. So let's just do a section cut at some location here and look at what the internal forces are looking like. So what have we got? Let's make a mark there and take an axis down like that. We've got our applied load 650, our applied torque T, so we know we're going to have a counteracting torque T and a counteracting normal force N. Okay, so that normal force N, that's going to create a normal stress that's going to be the same everywhere over that cut section. The internal torque T will create a shear stress, and that shear stress will be greatest at the circumference. So all points along the circumference will have maximum shear stress from the torque and normal stress from the normal force. So we want to analyze some point on the circumference of the element. Okay, so let's just pick any point here. Let's just make this point A that we're going to choose, and we'll draw the volumetric element for point A. Let's set up our axes before we do that. So this axis is going up like this one's going out, and this one's going out like that in that direction. So we've got X, Y, Z. Okay, so our element at point A is looking like this. Again, same as our example problem with the chalk, the face of the element that's in the section plane is the bottom one. So what are the stresses going to be on that? Well, we're going to have a shear stress from that torque. Here's tau. And then we're going to have a normal compressive stress from the internal normal force N. So here we go. We've got sigma. There we go. So let's put on our axes here. We've got X, Y, and Z. So we can label what these stresses would be labeled. This would be sigma subscript Y, and this shear stress would be tau Y. It's parallel to X, tau YX. Okay. So let's get values for what those stresses are. So we've got sigma Y is N over A, which is 650 kilonewtons times 10 to the 3 divided by pi over 4. What was our diameter there? 20 centimeters, 0.2 squared. And that gives us 20.7 megapascals. And then our shear stress, tau yx is T rho over J, and this is our variable T multiplied by rho, so the distance that our point of interest, point A, is away from the center of rotation or the centroid of that cross section, so that's the radius, 10 centimeters. 0.1 divided by pi over 2, 0.1, and raise that to the fourth power. So that's going to give us 636.6 multiplied by t, where t is being measured in Newton meters. Okay. So let's keep going here. Now that we've got those, we want to draw Moore's circle here. So let's draw what our in-plane representation of that volumetric element looks like. So we want to, or one of the options we could do is just look down the z-axis to draw this in the xy plane. Okay, so doing that, we'd have drawing like this, where we've got our shear stress would be upward on the right hand side. Go. And we've got our compressive normal stress. And this is x, y, and we have values for these here. Sigma y is 20.7 MPa, and tau is equal to 636.6 T. And again, that's coming out in pascals from that equation if T is in Newton meters. So let's remember that. So that's in units of pascals there. Okay, so let's go ahead and plot Moore's circle. Then we'll set up our axes here. Maybe we'll try and draw nice straight lines for this one. Okay, and we have normal stress, positive shear stress is downwards. Okay, the first thing we need to do is plot our average normal stress, or find our average normal stress to calculate, or to determine where the center of the circle is going to be. So that's 1/2 sigma x is 0 plus sigma y, that's minus 20.7. So we've got minus 10.3 there if you keep all your decimal places, MPa. So that means the center of our circle is located at minus 10.3, 0. So let's put that on. There we go. We'll call that minus 10.3. And this is in megapascals. Okay. There we go. Center of our circle right there. Now, the reference point on the circumference of the circle, point A, is given by the stress that exists on the right-hand side of the element, which is no normal stress. Shear stress is upwards, so it's a positive. So we have 636.6 T. Now, looking at the normal stress being plotted in megapascals, if we want to plot this in megapascals too, we divide by 10 to the 6. There. So let's plot that shear stress. We don't know where it is, but that's okay. Let's call this 636.6 T divided by 10 to the 6. That's a 6 there. Okay, so this here is our reference point on the circumference of the circle, point A. And then our radius stretches from C to A like this. And then we can draw our circle. Okay, so, oh, that was pretty good. All right, so now we can see what the stresses are that we need to determine to solve this problem. So we've got one principal stress that is here. That's the smaller magnitude one, so that's sigma 2, and one principal stress out here that is sigma 1. So failure will occur when sigma 1 here exceeds the ultimate compressive strength, or sigma 2 exceeds the ultimate tensile strength, whichever occurs first or at a lower value of our applied torque T. So in order to get those stresses, we first need to calculate the radius, and then it's just simply the process of adding what the value of C is onto that radius. So let's just flip to a new page here, and we'll figure out what R is. R is the square root of, let's see, that distance there is 10.3. 10.3 squared plus, and then we've got this distance, 636.6 T. 636.6 T divided by 10 to the 6, and then square that, and then square root. Okay. And then what we're going to do is, to that expression, we won't bother cleaning it up here, but to that expression we'll add the value of the center of our circle to get sigma 1 and sigma 2. So let's first assume that failure occurs due to the ultimate, or the failure occurs due to compressive stress. So let's compare the value of sigma 1 to the ultimate compressive stress of the material. So assuming compressive failure, right? Then compressive failure will occur when the ultimate compressive strength divided by the safety factor becomes equal to the value of sigma 1. Okay, so the ultimate compressive strength was 30, nope. These should be reversed here. It doesn't make sense that the tensile strength would be larger for concrete than the compressive ultimate strength. So that was my mistake when I was setting up the questions. So we've got, this should be compressive strength, and this should be the ultimate tensile strength. There we go. So let's do compressive strength first. So 36 megapascals for the compressive strength. Here we go. 36 times 10 to the 6 divided by 1.2 for our safety factor equals sigma 1. So sigma 1 is going to be the value of the radius plus the value of the center of the circle here. So we've got 10.3 plus what we've got for R there. So 10.3 squared plus 636.6 T divided by 10 to the 6 squared power 1/2. Okay, solve for T. Okay, so for that we get, what do we get? We get 26.2 kilonewton meters. Okay, so we could let that torque go up to 26.2 kilonewton meters before we had compressive failure occurring from the compressive normal stress. Now let's see what T is, assuming that tensile failure occurs. So in this case, we've got sigma U tension, the ultimate tensile strength, divided by the safety factor, is going to be set equal to the second principal stress. All right. Here we've got, just remind ourselves, so 6 megapascals there. 6 times 10 to the 6, divide that by 1.2, set it equal to, so now we're taking the radius and we're subtracting the center of the circle, 10.3, to get the value of sigma 2. So we've got 10.3 squared plus 636.6 t divided by 10 to the 6 squared to the 1/2 minus 10.3. There we go. And if we solve that, we get 17.8 kilonewton meters. Okay, so the tensile failure will occur before compressive failure does. So the 17.8 is the maximum value of torque that we can apply to that column without failure occurring. Okay, so that's really all there is to it in terms of brittle material. Failure theory is very easy. You just compare the maximum normal stresses to the appropriate ultimate strengths, and you're done. So in the next lecture, we're going to start looking at failure of ductile materials. So I will see you then for lecture 16.